So today we are talking about exponential and logarithmic functions and their graphs. We're going to start with the simplest case, which is the parent function. No add-ons. And then we'll start looking at the transformed graphs. Shift it side to side or up and down. We can reflect it about an axis. We can stretch it or compress it. Yeah. But let's go ahead and start with the parent functions. So we have exponential and we have logarithmic. That is not very nice. There we go. So we will start with exponential. Exponential is called an exponential function because the independent variable is in the exponent. Y equals a number raised to our independent variable. Y equals b to the x. And we call it b because that is called the base of the exponential function. And we know the little number up here is called the exponent. And this is an exponential function because it's a variable that's in the exponent. Can I get a thumbs up if we've seen this before? Yes, good. Okay. Logarithmic functions or exponential functions have a buddy, the logarithmic function. Y equals log base b of x. And we know that these functions are inverses of each other. In that exponentials undo logarithms, logarithms undo exponentials. That's going to help us today looking at properties and graphs. That's going to help us next week when we start talking about how to solve them, solve those equations. Okay, so one tiny note before we get started. We are making an assumption for all of the functions today that b is positive. So b is bigger than 0. And that b is not equal to 1. So for all exponential functions and logarithmic functions we're looking at, we are making that assumption. B is positive, b is not equal to 1. Why don't I want b to be 1? If I have 1 to the x, what's my function going to look like? 1 to the 0 is what? 1. 1 to the 1 is 1. 1 squared is 1. 1 cubed is 1. Regardless of what my x is, I'm at a height of 1. What shape does that make? A line, a horizontal line. Yeah, 1 to the x is a linear function even though it's not in linear function form because it plots a flat line. So we are excluding bases being 1. That is not an interesting function. Very good. So let's look at some important properties of these functions. First, because they are invertible, they have an inverse function. I know that both of these guys are 1-to-1 functions. They are functions, meaning they pass the vertical line test. They're 1-to-1, meaning they also pass the horizontal line test. And to get between them, I take the x-axis and the y-axis and I flip them. All right, next we're going to look at asymptotes. Asymptotes. Exponential graphs have horizontal asymptotes. And y equals b to the x has a horizontal asymptote at y equals 0. if I come over to his inverse buddy, and I take the y-axis and the x-axis and I flip them, what type of asymptote is a log function going to have? A horizontal. And where is that horizontal asymptote going to be? I've taken y and x and I flipped them. X equals 0, yeah. Yeah. And we should continue to see this pattern. Next, we're going to look at domain and range. And we've probably seen exponential functions before. A quick sketch. I know exponential growth looks like this. I know exponential decay looks like this. In both of those cases, what's my domain? Who sees it? Very good, Ethan, yeah. Negative infinity to positive infinity. Goes in both directions on the left and right side of the graph, arrows on both sides. Good. Next, we need the range, so we're looking up to down, or down to up, rather. We're scanning vertically. Yes, Bruno? It does not go past 0. Very good. Because we have an asymptote, horizontal asymptote at y equals 0. So we know our smallest is 0 open. Where's the highest point? Infinity, because it's got an arrow up there. Yeah, good. I'm going to remove these sketches. For logarithms, if I want domain and range without even knowing what the graphs look like, I know they are inverses. When I switch x and y, what happens to domain and range? They flip. Yeah, so the domain of an exponential is the range of the logarithmic parent function. The range of the exponential parent function is the domain of the logarithmic parent function. These guys switch places because they are inverses. Yeah, good. Very good. Okay, we've got asymptotes, we've got domain and range. Let's look at our intercepts next. Intercepts help us graph. So x-intercept, y-intercept. We'll start with our exponential parent function. My exponential parent function has a horizontal asymptote at y equals 0. Does it have an x-intercept? No, it's got an asymptote there. It can't cross it. So this guy has none. Never going to cross the x-axis. We saw in that sketch we made just a minute ago that it approaches, never touches. Very good. The y-intercept is at 1. Because when I take a number and I raise it to the 0th power, my answer is 1. Anything to the 0th power is 1. And now we're going to do some thinking. I know to get from exponential to logarithmic, I take y and x and I flip their positions. What happens to those intercepts? They flip, yeah. So the x-intercept was none for exponential. That means my logarithmic should have none for y. If my y-intercept for exponentials was at 1, my x-intercept for logarithms should be at 1. Yes, Bruno? Yes. Which is why we're doing this, so you can see the pattern. That's why we're doing it together. Very good. We like patterns as mathematicians. They make us happy. Very good. For both of these functions, exponential and logarithmic, We can tell whether they are increasing or decreasing by looking at the base, b. If b is bigger than 1, for both of these, our graph should be increasing. Okay. If, and now we have a conundrum of I know that b should be positive, meaning he cannot be 0 or less than 0. So between 0 and 1, so a decimal or a fraction, our graph is decreasing. If I take 1/2 and I increase the power, that fraction gets smaller. 1/2 squared is 1/4. 1/2 cubed is 1/8. It's getting smaller and smaller. It's decreasing. That's true for both of them. There is one more thing I'd like to add to those separate lists, which is something that you probably didn't see before. I don't know if you saw it before. Each of these graphs has a key point that will help us graph them. And just like everything else, they are related. For an exponential, I'm going to scoot you back up for a second. If I take this expression and I plug in 1 for x, what is b to the 1? It's not 1. It's not 0. 5 to the 1 is 5. 10 to the 1 is 10. B to the 1 is b. Yeah. So this guy has a key point out. Whoops, that's not what I meant to do there. Back up there. At 1, b. Knowing where my asymptotes are, knowing where the intercept and key point are, knowing what the end behavior looks like, that's enough to sketch the graph. I really only need 2 points in asymptote and that end behavior. Most of these I can sketch without a table of values. We like these. If my exponential's key point is at 1b, I take x and y, I flip them. Where is this guy's key point? b1, yeah. b, 1. Good. Good. Let's look at what those 4 graphs look like, increasing and decreasing. Yeah? So for exponential, we can have b is bigger than 1 or between 0 and 1. And then we get the same thing for logs. We can have b is bigger than 1 or b is between 0 and 1. Give me 1 second and then I will deal with that. Oh, technology is wonderful. Has Julie come back yet? Yes. All right, so b is greater than 1. I know my exponential is increasing. I know it has an asymptote on the x-axis. So it looks like this. We'll see how much you remember. Gabe, where is the y-intercept of the parent exponential function? 0, 1. Perfect. That's at a height of 1. I know it has a key point somewhere over here at 1, b. No, the graph is not to scale. Please don't judge me. If it's decreasing, it's this graph, but flipped horizontally. It starts up high and then comes down low. Intercept is still 1. Key point is still at 1 comma b, but you'll notice that b is now lower than 1. B is less than 1. And now we get to practice our inverse skills. We're going to start with the increasing exponential graph. So we're going to take this graph here, and we're going to switch x and y. So what was a horizontal asymptote is now a vertical. And my graph is doing this. Yeah. Gerardo, where is that x-intercept? 1, perfect. And then our key point is the inverse of what it was over here. Instead of 1 comma b, I know I have a point at b comma 1. Input is b, output is a height of 1. Similar idea. We know this is decreasing. So this guy starts up here and comes down like this. Same y-intercept. Should b be to the left of 1 or right of 1? See, we're contemplating. Jade has a smirk on her face. Should it be to the left of 1 or the right of 1? Should b, our base, be to the left of 1 or the right of 1? Left. He's less than. Yeah. B is less than 1. My key point is back here. It's closer to the y-axis because b is now less than 1. And b is that x-coordinate, so it should be closer to the origin. Two key points and an asymptote. I have those 3 pieces. Pretty straightforward to graph. What we're going to do is practice transforming those graphs. We had 4 different transformations we could perform. Let's see who remembers. 4 different transformations. Megan, what's one way I can transform a graph? Vertical shift. Perfect. I can move it up and down. Vertical translation. Perfect. What else? What else? Jackie, what else? Got a vertical shift. What else? Horizontal shift. I can pick it up, drag it side to side. Perfect. That's 2. So we've got the translations out of the way. Luis, what else? A reflection. Perfect. And flip it upside down. Flip it side to side. Got one more. One more. Alan. You're right, we could do a rotation. We're not going to talk about those in pre-cal. So yes, that is a type of transformation, not one we're going to address in that class. That's like higher level math. Somebody else, what's that last one? We've got shifts, translations. We've got reflections. Yeah, the stretching, the vertical and the horizontal stretching. Very good. We're going to focus just on vertical stretches for this graph. But yeah, very good. So let's take a look at what those transformations look like for logs and exponentials. We're going to do exponentials today. We'll do logarithms when I see you on Thursday. deep breath. All right, so I know my parent function is y equals b to the x. I'm going to go through that list of transformations. So horizontal slides affect the x coordinate. We pick up a minus c. Vertical shifts, vertical translations. Outside, perfect, because we added on to the answer. We calculate our original y and then we just add some numbers to it. So plus d outside the exponential, good. And if I want to stretch or compress or I want to flip, what do I do? Yeah, number out in front. Same pattern you've been using since you first saw this with vertex form for quadratics back in Math 2. We're going to see that pattern over and over again. Yeah. So we are making the assumption in this case that b is bigger than 1. We're going to ignore the decreasing graphs for now. But the idea is the same. When you are evaluating transformations, you should apply them using PEMDAS. That's a plus. It's a very messy plus, but that is plus d. Plus d. When we're applying transformations, we have to follow the order of operations, just like when we evaluate any expression. So, looking at that expression, I don't see any exponents, so I'm ignoring the p. What should I start with? What comes after p in PEMDAS? Exponents. Very good. I need to look at the exponents. And in the exponent is that c, which I know represents horizontal shifts. So the very first thing that I'm going to look at is I'm going to look at my c. And remember that c changes sign. So in the formula, if I see x minus c, is that a shift to the left or the right? To the right, yeah, opposite what you'd think. If I see x plus c, that's a shift to the left. C always changes sign. It's always backwards. Very good, very good. So we've checked off the p, there's no parentheses. We've checked off the e for exponents. What comes next in PEMDAS? Bless you. Multiplication. Very good. I have to deal with that a out in front, times a. And there's two things that a does. First, if I look at the absolute value of a, that stretches and compresses my graph. It's going to take my graph and go stretch or squish. The other thing I have to worry about is the sign on a. If a is negative, what does that tell me I've done to my graph? Flip it, yeah. That's a vertical reflection. Takes an increasing graph, makes it decreasing. Takes a decreasing graph, makes it increasing. Flips it upside down. Very good. So we've done the P, we've done the E, we've done the M, and the D. What am I left with? The A and the S, the addition subtraction, which is the plus D at the end. So if D is positive, which direction am I shifting my graph? Up. Positive means up. If D is negative, means down. And the question is, how does that help us graph? The answer is pretty short, actually. I only need 3 pieces of information to graph. So the first thing I'm going to do is I'm going to apply my transformations to the 3 things that I need to graph, which are my intercept, my key point, and my asymptote. Should only have one of each. And we do them that way regardless of whether it's exponential or logarithmic. Look at what happens to the intercept. Look at what happens to the key point. Look at what happens to your asymptote. Yeah. Once those things have been transformed and stuck on a graph, you're just going to connect the points with a smooth curve. If you want, you can make a table of values and include some x values that are not already in there. We know table of values is our default if I don't remember how to graph something on site. Yeah, if I don't recognize the form of the equation. But if you recognize it's exponential, identify those points in that asymptote, connect the dots with a smooth curve. Yeah. And we've got time for one example, and then we'll pick up where we left off on Thursday. Yeah? I think once you see it, it'll be less intimidating than it looks. So let's do an example together, and then we'll do some more examples on Thursday. Stop touching each other. Pre-calculus is not a contact sport. Let go. Thank you. So first, exponential or logarithmic? Jordan, exponential or logarithmic? Exponential, because I don't see the word log anywhere up there. Good. This is going to be really obvious. It's going to be nice and clear for us. So we know it's a logarithmic. I can see that it's not a parent function because all I would see is 2 to the x. So this is a transformed exponential. I need to figure out how it's transformed. So I want you to take about 60 seconds in your small group and discuss what transformations do you see represented in that equation. I'll give you 60 seconds. Just enough time to finish this and maybe give you a little homework time. It did say your name, Ethan. Give me one transformation that you see represented in that equation. Down 3. Very good. I see a -3 tacked on at the end. Everything's going to get shifted down 3. Very good. Gerardo, what other transformation do you see represented up there? So remember, for those vertical compressions and stretches and that reflection, we're looking for a number out in front of the exponential. And here my base is 2, the exponent's x plus 1. There isn't anything in front of the 2. So in this case, there's no vertical stretch or compress. We're not reflecting. What's one thing we haven't addressed? Perfect. Yes, very good. Perfect. Changes sign, so positive is left, negative is right, opposite of what we think. Good. So we are picking up our parent function 2 to the x. We are shifting it left 1 and down 3. We're going to do that operation to our intercept, to our key point, to our asymptote. So the first thing I'm going to do is I'm going to jot down what those things look like for the parent function, what they look like for the new function. So intercept, key point, I think I know how to spell, and asymptote. So parent, new. All right. So we will start with the intercept. Where does the parent exponential have an intercept? Who remembers? Randy? Where is y equals b to the x have an intercept? You wrote it down. I heard a 1. Is that an x-intercept or a y-intercept? Yeah. That's a y-intercept. Key point is, I think, what I was hearing in the back corner, which is 1 comma b. And in this case, what is our b? What's the base of our exponential? 2. So 1 comma 2. Where is the asymptote for the parent exponential function? Bruno, on your paper, what does it say? Asymptote for the parent exponential. Vertical or horizontal? Did you write it down? You don't think you did, so let's pick on this side. Cecilia, vertical or horizontal? Did you write it down? Nobody wrote it down. Marissa? Horizontal, very good. Specifically at y equals 0. Exponentials have horizontals. Now I want to do 2 things to each of those. I want to shift it left 1, down 3. Left 1, down 3. So for my intercept, left 1, what's my new x coordinate going to be? -1. Down 3, my new y is going to be -2. Perfect. I'm going to do the same thing to the key point. I go back 1, that puts me at 0. I go down 3, that puts me at -1. For my asymptote, which is horizontal, is it affected by the shift left 1? No. So the only thing I have to worry about with my horizontal asymptote is the fact that my whole graph is dropping down 3, including the asymptote. That is enough for us to get a sketch of our graph. So let's do that. So first thing, I'm going to draw my asymptote. I'm going to mark my points. I'm going to draw a smooth curve. So I have an asymptote at, I guess I should scale this, 1, 2, 3. I have an asymptote at -3. And then I have a key point at 0, -1. And I have an intercept, or what was a former intercept, at -1, -2. Left and down, left and down. My base, B, is 2. Is this an increasing graph or a decreasing graph? Increasing. Good. My base is bigger than 1. So I know that it's going to start out close to that asymptote, and then it's going to pass through those points. Way less work than graphing a rational function, yeah? Nice breath of fresh air after rational functions. You will notice when you try the same thing in Delta Math for your homework, it's going to baby step you through it by having you fill out a table of values where it's going to give you the x coordinate, it's going to have you evaluate the parent function, and then each transformation one at a time. It's going to walk you through that PEMDAS step. When I see you on Thursday, because you guys are an odd period, we will go over the same thing for logarithms. We'll do some examples, and then I'll have some practice problems in your small group. If you have questions, send me an email or catch me tomorrow before or after school. We're not leaving for another couple minutes, but I'm done. Oh, hey, perfect. Yeah, come on up, Ellie.